Let's study radioactive decay. Remember that the emission of radiation from the nucleus is always spontaneous and random. Like, what does it mean when I say it's spontaneous and random? That means it's going to happen suddenly and it's going to happen randomly. Then let's talk about the decay constant. Decay constant is the fundamental parameter in the radioactive decay, and you can say that this is the probability of the nucleus decaying per unit time. So, let us see this in detail. What did I say? I said that the decay constant is the number of nuclei decaying per unit time, and we have to divide that by the total number of nuclei present. So therefore, decay constant is fractional change in the number of nuclei, delta n over n per unit time, and we can write the equation for the decay constant, which come up to be delta n over n times delta t. Now, if you just see this carefully, you have seen that there is a minus sign. What does this minus sign indicates? It tells you that the number of radioactive nuclei in a sample of material decreases with time. That is why we are having a negative sign. So what is the unit of decay constant? It's per second. So if you want to see this in a dice decay, we can say that it's 1/6 per throw every time the dice are thrown, or on average it's 1/6 of them if you take the turns of 6. So this equation can also be written as delta n over delta t is equal to minus decay constant times the n. So we can say that the number of nuclei decaying per second is equal to decay constant times the number of nuclei. Now let me tell you that this actually leads us to the definition of activity of a radioactive source, which is the number of emissions per second. So we can say activity is equal to decay constant times the n, where A is the activity, and remember what is the unit for activity? It's becquerel, and it's the rate of decay, 1 disintegration per second. So be very careful when recognizing about the activity. Its unit is becquerel, and what is it? It's the number rate of decay or integrations per second. So decay constant can also be solved up to give us some other equations as well. You know that number of nuclei decaying per second is equal to the product of the decay constant times the number of nuclei. So this equation can be solved by separating the variables and integrating them on both the sides. So now the limits of integration are from 2n for the nuclei and from 0 to t for the time. So therefore, we will end up for our final equation, which comes up to be n is equal to n naught times log minus decay constant times t. Now in this equation here, n is the number of nuclei in the radioactive sample at time t, and n naught is the number of nuclei at time 0. So which is the time that we start to observe the sample of nuclei. Okay, so the final equation which is for you here, n equal to n naught log E minus raised to power minus decay constant times t. Now let us see this example, that how are you going to solve few questions coming up from this part of the physics. So, you know, a sample of radioactive decay material, it contains, for example, 100 times 10 raised to power 12. The nuclei have a decay constant of about 0.01 per second. You have to predict the number of nuclei remaining after 10 seconds. So you know what they have given us. They have given us a radioactive material which is equal to 100 times 10 raised to power 12. They have given us the decay constant which is equal to 0.01 per second, and then they have also given us the time which is equal to 10 seconds. Right? So how can you find out the number of nuclei? And number of nuclei could be found out by n is equal to n naught, this formula, log my raised to power minus decay constant times t. We know that the time 0, that means at the start, we have the sample which contains about 100 times 10 raised to power 12 nuclei. We're just going to substitute that. We know that decay constant is 0.01, which they have already given us. Time is also given, which is 10. So our number of nuclei is what? If we just solve this question, we come to know that our number of nuclei is 9 times 10 raised to power 13 nuclei after 10 seconds. So let's talk about the half-life now. What is half-life? Half-life is the initial number of nuclei to decay. Half-life could be extremely short, which is a fraction of a second, or it could be extremely long, which means it could be a billion of years. And remember that after one half-life, you will have half of what you initially started with. And after two half-life, you will have a quarter of what you will initially start. And after three half-lives, quarter of initial nuclei remains, and so on. Okay. And then we'll simply see. So you can say that after one half-life, there will be n naught over 2 nuclei left. So we know that n naught over 2 will be equal to n naught E minus decay constant times T O divided by 2. Now, if you just solve this one, taking the log on both of the sides, we end up with a final equation which tells us that half-life is equal to 0.69 over the decay constant. And it is very important for you to remember these final equations. You're going to see a few questions coming up from this part of the half-life. Now, the concept of half-life that we have just discussed here, now what is the concept, okay? We have numerous implications about this in various fields. Like for example, if you understand the half-life, you know that you can actually store some waste for how long. It actually helps us to determine the optimal storage time and it conditions to minimize the radiation exposure. And it can also be used to date rocks and fossils and artifacts. So by measuring the decay of the isotopes, for example, the carbon-14, uranium-230 and potassium-40, scientists were able to age the samples. Third is about the nuclear medicine. Specific half-lives are used for this diagnosis and treatment. Like for example, technetium-99m is having a half-life of about 6 hours. It's actually used for imaging. And similarly, for example, the iodine-131, it has a half-life of about 8 days. So therefore, it is mostly used for the thyroid treatment, for the diagnosis definitely, and sometimes for the treatment as well, because this iodine-131, it stays in the body for 8 days. Therefore, definitely it can proceed with the treatment within our body for 8 days. Then food irradiations. For example, gamma radiation is used to sterilize food. Okay, half-life is definitely essential for calculating the required radiation dose. Then comes the radiation safety. So in order to understand the half-life, it helps to protect the people from radiation exposure. It informs the safety protocols for handling radioactive material and managing radiation emergencies. Then comes the environmental monitoring as well. Half-life is definitely used to study the movement and the distribution of radioactive isotopes in the environment. And it is also used for geological research. Half-life helps scientists study Earth history, for example, geological events in the climate change. Then comes industrial applications. Radioisotopes are used for various industrial processes such as sterilization, food irradiations, and materials modification, definitely.